Welcome back, everybody, for another exciting lesson with the amazing Mr. A. Trying something new, recording with my sweet official Apple AirPods, just so you know what I'm repping over here. Today's lesson, we're going to be covering limiting reactants. So it's kind of like the next step in our reaction stoichiometry chapter. Now, so far, based on the lessons we've had previously, you should be able to answer questions like this. So, given some balanced equation, giving you this question, if 6.7 grams of phosphoric acid are reacting, how many moles of calcium phosphate can be produced? And if this looks familiar, well, that's because I just kind of stole it from my last lesson at the end there. Don't fix something that ain't broke. Now, if you wanted to solve this problem, right, we deal with it kind of like dimensional analysis, determine where we're starting, where we want to go. So I think last time I kind of color coded a little bit, make it nice and pretty, if you will. I thought it was kind of cool because there's a little bit of a little color to our life here. Now, we start with 6.7 grams of phosphoric acid, and we want to get to, what is it, moles of calcium phosphate. Just fits. All right. So, in order to do this problem, we would have to convert grams to moles. Remember, it's always important that we convert our information into moles, or given information into moles, so we can use the mole ratios. So, should have been a little bit better prepared here because I do not know the molar mass of phosphoric acid by heart. But I do know, since we're converting from grams to moles, we need to divide by the molar mass. And once we do that, we need to use a mole ratio to convert to moles of calcium phosphate. Sorry if that's not the neatest. All right, so this mole ratio right here, I'm going to look up at the balanced equation. 2 moles of phosphoric acid, 1 mole of calcium phosphate. Let's put those in. Keep the colors. Let's make this one green. Why not? And this one is yellow. So, just using the units without getting that mass value, I would see that the units of grams cancel out, units of moles of phosphoric acid cancel out, and we would be left with units of moles of calcium phosphate. So let me just get the molar mass so we can finish this bad boy right here. Let's just say it's 98 for short. So in your calculator, you should be doing 6.7 divided by 98 divided by 2. That's something like 0.03 moles of calcium phosphate. Alrighty, so we should be able to solve these problems. Now, these aren't the problems we are going to be dealing with. We are going to need to consider more than just one reactant. Because, well, we have 2. If we were talking about like our baking cake or baking cookies kind of, what do you call it, analogy, right? When you're making cookies, let's just say we had a cookie recipe here, and we knew it took 2 cups of sugar, oh, and 4 cups of flour. Okay. Now, let's say you went to look in your cupboard or in the pantry, and you saw you only have 3 cups of flour. Oh, no, you can't follow the recipe just the way it is, but perhaps you can still make some cookies. Now, are you just going to assume you have enough sugar? No, you cannot, because you never know if you have enough sugar too. So, same idea. Now we're going to relate that to chemistry. Alrighty. So that's the idea of the limiting reactant. And I'll have another kind of analogy for us in just a bit here. All right. So here is the concept of limiting reactants. So limiting reactants, also seen as reagents. The reactant that runs out first is important. So it's the reactant that runs out first. So limiting reactant is the reactant that runs out first and limits the amount of product made. Okay, that's pretty much all we need to know. Down here it says determine how much product can be formed, blah, 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 blah. That'll probably make more sense once we start doing these problems. But most important for these problems is that we determine what our limiting reactant is, because that will also determine, so our limiting reactant will determine how much product can be made. And yes, I did have to write that. And that's pretty much what that second bullet says. I'm realizing that now. You know, it's a learning process. Work with me. Anyways, like I said, I have another analogy for you. Let's say to make a car. Well, what do cars consist of? They have 1 engine, 4 wheels, and I don't know, 2 axles. Almost forgot how to spell axles. Still not sure if that's right. Anyways, let's say you're running a car manufacturer or car making shop, whatever that is. And in the shop, you realize you have 3 engines, 16 wheels, and 100 axles. All right, got a really good deal on those axles, bought them in bulk. Sweet. Now, looking here, we can see how many cars we can make. How do we do that? Well, we look at each individual component, so each of our reactants, if we want to say reactants in our car making recipe, equation, whatever you want to call it. So 3 engines. Well, I know that in a car, it takes only 1 engine. So if we have 3 engines, we can make 3 cars. Now for 1 car again, we know that you need 4 wheels. We have 16 wheels. So we can make 16 divided by 4 cars with 16 wheels. Last, we know each car needs 2 axles. We have 100. 100 divided by 2, we can make 50 cars with 100 axles. Now, let's say your boss comes and say, hey, we have all these materials. How many cars can we make? Are you going to say 50, 4, or 3? Well, you're going to have to say 3, right? 3, because we are limited by the number of engines we have. We could have made 50 whole cars with 100 axles, but we don't have enough of the other components, right? We could have made 4 cars, but we don't have enough engines. So what's limiting our car manufacturing ability? The engines. So we're going to apply this now to chemical equations. So there's 2 main approaches to determining your limiting reactant or limiting reagent in a reaction. And here's the first one. So there's little 5 steps. The main thing with this one is we're going to be comparing the amount of reactants needed. In approach 2, we're going to be looking at how much product each reactant can make. So you'll see the difference between those two once we kind of get through this lesson. Now, in this first approach, we want to find limiting reagent by looking at the number of moles of each reactant. Okay, so we're going to compare with the mole ratios that we know from the balanced equation to the ratios that we actually have given in the question. All right, so let's just get down to it. Here's a nice, wonderful example question for us. It says, consider respiration, one of the most common chemical reactions on Earth. Respiration, that's like when the rains fall down in Africa. Well, I think we should bless those. Or is it something else? I don't know. Anyways, let's just get to it. Question says, given this equation here for respiration, what mass of carbon dioxide, so let's underline that right there, might be important, mass of carbon dioxide forms in the reaction of 25 grams of glucose and 40 grams of oxygen. So here we have 25 grams of glucose. This is glucose. 40 grams of oxygen. That's oxygen. And mass of carbon dioxide. That's carbon dioxide. So now, in this question, different from what we've had before, they're giving us the amounts of both reactants. So what we need to do is determine which reactant is limiting us, and then use that reactant to determine the mass of carbon dioxide that can form. So let's go through the steps. Step 1, determine the balanced chemical equation for the chemical reaction and determine relevant mole ratios. So we have the chemical equation, and I'll just rewrite it so it's a little bit more clear here. And I'm not going to include that energy part because we just don't need it right now. So, surprise, it's already balanced. That's nice. My students know they should never expect that surprise in my class. No free passes. You earn it. You know what I'm saying, dog? Anyways, balanced equation. Now that we balanced it, we need to write the mole ratios. Relevant mole ratios. Now, when it says relevant mole ratios, we kind of have to think about it. What components are we dealing with? we're dealing with glucose, oxygen, and carbon dioxide. We're not worried about H2O. Unless you are feeling dehydrated, then you should definitely worry about H2O. Make sure you drink enough water every day. 8 cups a day keeps the dehydration away. But right now, we're not worried about that. So maybe that makes things a little bit faster for us. When we're writing these mole ratios, we know we don't need to consider H2O. So let's just write down what we need. So mole ratios here and here. So only 3 of them. That's not bad. All right. So 1 mole of glucose for every 6 moles of oxygen gas. 1 mole of glucose. Good old glucose. Keeping me energized. Right? I don't know. 6 moles of CO2. And lastly, 6 moles of oxygen gas for 6 moles of CO2. Alrighty, so there's our 3 relevant mole ratios, right? Remember, relevant meaning we only care about what's given to us in the question. So now we move on. Step 2. Convert all given information into moles, most likely through the use of molar mass as a conversion factor. Alrighty, so what information is given to us? Looking up here, we can see that we are given, let's see how this brown looks, 25 grams of glucose and 40 grams of oxygen. Remind me never to use that color highlighter again. Oh my gosh. Anyways, let's write those down. So, 25 grams of glucose. And we have, what's the other one again? 40 grams of oxygen. You know, getting in my old age here. Can't remember 2 seconds ago. I don't even know what time it is. What year is it? Anyways, enough about that. So we are starting in grams. We want to convert to moles. So what do we need to do? Well, thanks for asking myself. What we need to do is find the molar mass of each of these components and divide by those. So the molar mass of glucose, simplicity reason, I'm just going to round it, is 180 grams per mole. For O2, 2 oxygens, so it's not 16, it is 32 grams. All right. Wonderful. So now we just do the math here. 25 divided by 180. Get a 0.139 moles of glucose. And then we do 40 divided by 32. 1.25 moles of O2. All right, so now we have, or now we know, I should say, the amount of moles of each component that we are given. Okay, so we're getting closer to determining which one of these is our limiting reactant. So now, that's awkward. The answers are right there. Anyways, moving on to step 3. Now that we know how many moles of each component we have, what we're going to do is see if we used up all of each, or all of the first component, how much of the second component would we need, and vice versa. So let me show you what that means. So if all of the 1.25 moles of oxygen were to be used, all right, so we know we have 1.25 moles of O2. Now with these kind of little sub questions, these go more back towards what we learned before in the previous lessons. Given one piece of information, find another piece of information. So it's only one conversion from moles of O2, and in this case, the other reactant is moles of glucose. And we're going to do the similar thing down here. Instead, we're going to start with the glucose amount that we are given. Oops, not grams. Come on. And we're going to want to get to moles of O2. So, how do we do this? We need our mole ratios and what compares glucose and oxygen is this mole ratio right here. So let's use that one. Mole ratio is 1 mole C6H12O6 for 6 moles of O2. Down here, using that same mole ratio but flipped, we are going to write it this way. Those cancel out. Those cancel out. So 1.25 divided by 6. We'll get 0.21. And then 0.1388 times 6 is 0.83. All right. So let's just look at what we did here. So what we did in this first step, what we did is said, if we use all of our O2, we're going to need 0.21 moles of glucose. And in the second equation, what we found out is, let me keep it same language. If we use all of our glucose, come on, we need 0.83 moles of O2. Okay, so looking at this first statement here, we need 0.21 moles of glucose. How many moles of glucose do we have? That is all the way back up here. We only have 0.139 moles of glucose. So, do we have enough? No, we do not. No, we do not. Not enough. It's sad. It's sad times. Sad boy hours. Let's put a little tear there too, just so we know it's the real deal. Looking at our second statement, we need 0.83 moles of O2. How many do we have? Well, it's over here. We have 1.25 moles of O2. Is that enough? Yes, indeed, we have enough. Have enough. And now we're happy boys and girls, of course. So, the limiting reactant in this equation is glucose. So right here, glucose is our limiting reactant. And we determine that because we don't have enough glucose based on the amount of oxygen we have. So now that we determined that 0.139 moles of glucose is our limiting reactant, we're going to use that to calculate the amount of each product that can be produced. Remember, the limiting reactant determines how much product can be produced. So, since we have two products, we're going to have two lines of equations, both starting with our limiting reactant, like so. Now, if I remember correctly, the question actually only asks for the mass of carbon dioxide. So I'm just going to do one line here. I'm just going to pretend that it doesn't say H2O, because remember, we said we're ignoring H2O. I don't need it. Water. I don't need it. Shout out to my boy SpongeBob one time. Anyways, so first thing to do to get towards grams of carbon dioxide is to convert to moles of carbon dioxide. We do that by using a mole ratio. Which mole ratio? Well, I'm thinking this one. So let's use that here. 6 moles CO2, 1 mole glucose, and it would be in terms of moles of CO2, but we don't want moles, we want grams. So we need to multiply by the molar mass of carbon dioxide, which hopefully is about 32 plus 12, 44 grams per mole, which would leave us in units of grams of carbon dioxide, which is exactly what we want. So now we just do the math. 0.139 times 6 times 44, and we will get about, I'm just going to round it, 37 grams of carbon dioxide. So, answering this question here, what mass of carbon dioxide forms in the reaction of 25 grams of glucose, 40 grams of oxygen? We had to do all of these steps to determine that we could make 37 grams of carbon dioxide given those two amounts of reactants. It looks maybe like a lot, but I promise you it's not too bad. Right? It's just a lot of multiplication, division, a lot of ratios, a lot of comparing. Nothing you haven't learned. We're just applying it to chemistry. So I don't want you to be too scared. All right, just a couple times practicing, couple practice problems, and you'll be an all-star. Hey now, you're an all-star. So, now that we finished this method, we're going to move on to approach 2 and do one more example problem. So, in approach 2, this is my preferred approach because it kind of leads you to the answer a lot more directly for most of these questions. Because instead of comparing the amounts of reactants that we have. So instead of doing this step 2, and this step 3 here, what we do is just assume we have enough of the other reactant while testing the amount of the first reactant. And you kind of see what I mean by that when we're doing this problem. And you'll see what I mean by it more directly gets to our answer. Okay, so here's approach 2 again, and we're going to go through these steps together. So let's get to it. Example 1.2. Calculate the mass of magnesium oxide possible if 2.40 grams of magnesium are reacting with 10 grams of oxygen gas. And they give us the equation here. So just to rewrite that, magnesium, oxygen, magnesium, oxide. So first step, always balance your equation. So let's just do a little trickery there, and bing, bang, boom, we got a balanced equation. Now that we have a balanced equation, it's probably good practice for us to write down the mole ratios. Now, it doesn't say that step here, but we should always do that anyways. So let's just do those really quickly. 2 moles of magnesium for 1 mole of 2 moles Mg, 2 moles MgO, 1 mole oxygen gas, 2 moles magnesium oxide. Alrighty. Now we have our mole ratios. We're ready to get stoiched on this stoichiometry. So next step. Again, important step. Convert the given information into moles. So we're given 2.40 grams of magnesium and 10.0 grams of O2. So since we're given the mass values in grams, right, we need to divide by the molar masses. So magnesium's molar mass is 24.3 grams per mole. Oxygen gas mass, molar mass is 32 grams per mole. So hopefully doing some relatively quick maths and getting these wonderful, wonderful answers. Or maybe I'm just doing this wrong and this is just completely awkward. And yeah, let's hope that's not the case. Okay, if you did some magic, if you used a calculator, if you used your amazing brain powers, you would get these mole values for magnesium and oxygen gas. So we are on our way to solving this problem. So let's move on to step 3 now. Use stoichiometry. It's like some kind of like spell, maybe like, your boy HP Harry Potter starting out Wingardium stoichiometry or something like that. You never know. Science is just explained magic, really. I believe Sir Albert Einstein said that. I don't even know if he's a sir. I know Elton John's a sir. He was knighted. That's pretty cool. I want to be knighted. Anyways, use stoichiometry to determine the mass of a product that each reactant could make. So, in this specific question, there's only one product being made, right? It's only magnesium oxide. Now, if there was 2 products being made or more, what you would do is just choose one. Choose one so we have a comparison point. In this case, it's the illusion of choice, right? Because there's only one choice here. So what we're going to do is assume, well, let me write it down first and then explain. So what we're going to do is have two lines of calculations here, starting with the amount of each component that we're given. All right. So now each question, or I'm sorry, each line is going to be kind of like one of the questions we had from the previous lessons. So for this first line here, you can imagine a question saying, if you're given 0.099 moles of magnesium, how many moles of magnesium oxide can you make? Sorry. And then with this second one, you're going to pretend you have a question saying, if you have 0.313 moles of O2, how many moles of magnesium oxide can you make? In both of those questions, we're not worried about the other reactant. We're assuming we have enough of the other reactant. All right, so let's go ahead and do those problems now. So first one, we have 0.099 moles of magnesium, and we're going to assume we have enough oxygen. So I'm looking for a mole ratio to compare magnesium and magnesium oxide. Right there, 2 to 2, and I think I can do this one in my head. We end up with 0.099 moles of magnesium oxide. I'm just going to fix that M there because I don't even know what that is. All right. Now, same thing for this second part. We're going to assume we have enough magnesium and say, well, how much magnesium oxide can we make if we have 0.313 moles of oxygen? Oops, that's not right. I meant to use this one. So this is the wonderful mole ratio we're going to use here. Alrighty, and this says 2 moles MgO, 1 mole, 2, and this one, I might be able to do this in my head also. 626 moles of O2. Oh, not O2. Just kidding. MgO. Isn't there a band? It's like MgO. I don't know. Anyways. So, what we did again in this first one, we assumed if we had enough oxygen gas and 0.099 moles of magnesium, we could make 0.099 moles of magnesium oxide. In the second line, if we had enough magnesium and we only had 0.313 moles of oxygen gas, we could make 0.626 moles of magnesium oxide. So, which reactant is going to make the least amount of product is what we're looking for. That reactant is magnesium. So magnesium is limiting our production of magnesium oxide, right? Because if we were able to use up all of the O2, we could have made that much magnesium oxide. But since we only have this much magnesium, we're only going to be able to make that much magnesium oxide. So again, that's why I kind of like this approach more, is because typically your question is going to ask mass of product or mole of product. So by doing this, we're finding what the limiting reactant is and the moles of the product made. Remember, the limiting reactant will determine what how much product is made. Right? So that's why I'm circling this 0.099 moles of magnesium oxide, because that's the actual amount of magnesium oxide made. We can't make 0.626 moles because we don't have enough magnesium. So to answer these other questions here, the reactant that produces a smaller amount of product is a limiting reactant or reagent. That is magnesium. Now, introducing a new keyword, excess reagent, excess reactant. That's the one that produces the larger amount in this case. That's O2, right? And what it means by excess reactant is, well, we're not going to be using all 0.313 moles of O2 because that's more than enough, right? If we used all of this, we would be making that much magnesium oxide, but we're only making that much. So obviously we're going to have some O2 left over. So that's why it's called our excess reagent, excess reactant. So questions, follow-up questions for these questions could be, well, how much of that excess reactant do you have left over? Right? Maybe, hey, we want to know how much oxygen's left over so we can do another reaction with it later on. Or, I don't know, maybe we could return some oxygen, give it back to the Costco oxygen. You know, they accept returns that are like over 10 years old. I mean, such a great return policy, right? Anyways, find the amount of remaining excess reactant by subtracting the mass of the excess reactant consumed from the total mass of the reactant given. All right, mass of excess reagent calculated using the limiting reagent. Okay, so for this first one, I guess there's technically, I guess you could say there's two possibilities. In doing this, I think that we're going to not worry about this. Actually, I'm just going to do it anyways. So, in this first one, we're going to use the information that's given to us. So we know that we have 10 grams. So we're given 10.0 grams of O2. All right. So we need to figure out, well, how much of the O2 did we actually use? So the way we're going to do that is by calculating that using the limiting reagent. So our limiting reagent is 0.09. So I'm going to put used. So it's 0.099 moles of magnesium. And we need to figure out how many grams of O2 we're using. So, just like the other problems that we've been working out with, we need to get to moles of O2 first, and then we can get to grams of O2. So, we're going to use this wonderful mole ratio. And we have 1 mole O2 for 2 moles of magnesium. That's an M. And then we need to multiply by the molar mass of O2, which is 32 grams per mole. So, doing the math, 0.099 divided by 2 times 32 gives us 1.6 grams of O2. this is how much is used. So we take the given minus the used, which is 10.0 minus 1.6 equals, 8.4 grams of O2 excess. So we were given all of this O2. We only used this much here. So we have this much left over. Alrighty. So that's one way to calculate it. Another way, let me just delete this. Another way to do this is to use the mass of the product to calculate the mass of the excess reactant used. So, still the same thing. We're given 10.0 grams of O2. So really all this is just two different ways to calculate how much we used. So in this case, we're using the mass of the product. All right, so the mass of the product, well, I know the moles of the product actually, which might be better for us. So we know we made 0.099 moles of magnesium oxide. So now it's just kind of a different starting point for us. So in the first method, we're starting with moles or mass of our limiting reactant. In the second method, we're starting with moles or mass of our product that's actually made. Remember, we actually made 0.099 moles of magnesium oxide because we were limited by the amount of magnesium that we have. So if we do the work here, you'll recognize that numerically it's the same exact thing as the previous method. Only thing that changed was our starting units. In terms of moles of magnesium oxide instead of moles of magnesium. So again, we're going to see that we had used 1.6 grams of O2. So subtract that from the given. And once more, we see that we have this much excess O2. Alrighty. So I will be uploading a second video pertaining to limiting reactants, and it's just going to have some sample problems. You saw me delete one here. There's a second one. So I might have 2, maybe 3 questions there. Just for more practice for you to see. When I'm doing these problems, most likely, I'm going to be doing approach 2. Again, remember I said I like it because of this step right here. Step 3, we're calculating the mass of the product. Most usually, your question is going to be asking what the mass of the product is that's made. So by doing approach 2, we're kind of killing 2 stones with 1 bird by determining what our limiting reactant is and also finding the amount of product made. So look for that next video. I'm sure it'll be uploaded pretty soon after this one. Hope you enjoyed. Hope this was fun for you because it was certainly fun for me. It's been nice to hear some of my students saying that they actually enjoy this, which makes it worth my time to do this because it does take a little bit of time, but you know, I gotta share that knowledge. There's so much in this brain of mine. I gotta get it out there or else my head might explode. So, hope you enjoyed again. Make sure you like, subscribe, and let's see. Oh, let me give a little dimension here. Wait, hold on. This is gonna get better. Quite the artiste, if I may say. Like, subscribe, and hit that golden bell. That way, you can be notified every time I drop a new sick vid. As always, I am Mr. Amazing Mr. A, and I will talk to you, kids, adults,